So, good afternoon, ladies and gentlemen, especially for our guests from outside the Academia Sinica, as well as our distinguished guest, Professor Kajita. So today is one of the Taiwan Bridges series of lectures to be given by Professor Kajita. And I'm Henry Huang from the Institute of Physics of Academia Sinica. I and Kajita-san share the same broad research orientations of neutrino physics. And I have the very great pleasure and as well as honor to be the front row witness of some of the groundbreaking work that Kajita-san and his team and his laboratory has produced in the past 3 decades. So it was a really thrill to go through this era. And before I go into more details to introduce the speaker, let us get our Vice President, Professor Chung to come and give us a few words of welcoming notes, as well as remind us of the context of this bridge series. Thank you.
Okay, good afternoon, our distinguished guests, colleagues, ladies and gentlemen. Yeah, I would like to welcome you to today's event under Taiwan Bridges program. Okay, Academia Sinica, together with 11 other universities, is participating in this very special program in collaboration of the International Peace Foundation. It is designed to bring over 30 Nobel laureates to Taiwan within a period of 6 months. And we hope that through these lectures, we could foster dialogue on important subjects related to science, humanity, and our future. Academia Sinica is hosting 10 lectures under this program. And this is the 10th one today, and a concluding one, but we are extremely honored to have Professor Takaaki, I hope I pronounced that correctly, Kajita from the University of Tokyo, and also the 2015 Nobel Laureate for Physics for the discovery of neutrino oscillations. I think probably for non-physicists, this may sound very peculiar because this discovery proves that neutrinos, which is just are some kind of fundamental particles, have mass. And that demonstrated that our standard model for particle physics is incomplete. Okay, so what is the real story? I think that's still something that we need to work on in physics. Okay, we're going to hear more introduction on Professor Kajita later by Dr. Wang. But we know that he has devoted his career to the study of neutrino physics and also gravitational waves. Okay, those are very important subjects in physics. They need very forward-looking scientific vision, and also the support of large facilities to carry out those studies. Okay. So in the instruction of those large facilities, and also in the afterwards for the analysis of the data collected by those facilities, and we need to put together physicists, scientists, engineers to work together from everywhere in this world. Okay, so that's why Professor Kajita is going to talk about international collaboration in basic science, which is a very important part in order to advance our knowledge, our endeavor in those fundamental research. Okay. Again, on behalf of Academia Sinica, we'd like to thank Professor Kajita for the lecture today, and hopefully we'll learn a lot from his own experience. And let us welcome Professor Kajita, and Thank you.
So let me introduce our distinguished guest and speaker for this afternoon. Professor Takaaki Kajita is a senior scientist from the University of Tokyo, as well as the world-famous Institute of Cosmic Ray Research, which is attached to the University of Tokyo. It is a very famous and very productive research laboratory that is admired worldwide. Over several decades, Kajita-san, together with his colleagues and generations of students and both international and domestic students, have built and operated the Kamioka Underground Laboratory in Japan, as well as formulated and operated several generations of experiments of different directions in this laboratory. And you will hear much more, I'm sure, that about the story, the evolutions of this laboratory. Through this several decades of tremendous groundbreaking work, they have made tremendous contributions to almost every subject that they touch upon, including the discovery of the neutrino mass through the observations of through the first observation of atmospheric neutrino oscillations, which is likely the theme of one of the main discussions here, with which Professor Kajita, together with Professor Madonna, who was with us in the bridge program a month ago, was awarded the Nobel Prize of Physics in 2015. And this, I remind that this is the second Nobel Prizes from the Kamioka laboratory. Not that many laboratories can discuss Nobel Prize in plural from prizes. So on this is a huge success and then admiration throughout the world. And together in today's context, in addition to being producing groundbreaking sciences, the trail-blasting success of the Kamioka laboratory and program, in fact, inspire and catalyze many of the developments throughout the world, especially in Asia. Some of the domestic programs, facilities that has been built in Asia can trace its root to the inspirations of the success of the Kamioka program. So the impact is beyond neutrino physics, is on the development of science. And for today, Kajita-san would, in his lecture, would of course focus on the narrative of the Kamioka story, but with the context of international collaborations. So, which is tries to, from his experience, tries to use the Kamioka narratives to set the stage to discuss something even grander about international and collaboration. These are two different aspects, important aspects of the modern day science, and we pretty much look forward to the experience from Kamioka and then see what that can further inspire us beyond neutrinos, beyond underground physics, but in the context, in the operating systems of how science is organized. So, Kajita-san, the floor is yours, and we very much look forward to your insight on international collaboration through the tremendously successful Kamioka story. Thank you.
Good afternoon. First of all, thank you very much for the kind introduction. Well, today, I want to talk about international collaboration in basic science based on my experience. Okay, well, this is the outline of this talk. First, I want to briefly discuss my research history. Then, I want to discuss neutrino research in Kamioka, Kamiokande, Super Kamiokande, and also at the end of this section, I want to talk about the next generation experiment in Kamioka. Then I'd like to move on to other topic, that is gravitational waves. And in particular, I want to talk about our collaboration, which is called Kagura. Then I'll summarize this talk. Okay, first, I'd like to tell you my research history, which is actually quite simple. Well, I became a graduate course student in 1981, and at that time, I joined the Kamiokande experiment. At the time, this experiment was still in a preparation stage. Anyway, I was a member of the Kamiokande experiment, and this experiment continued until the spring of 1996. And at that point, our main experiment was changed to Super Kamiokande, and I worked in this experiment for more than 10 years. Then, slightly before 2010, I decided to change my research topic from neutrinos to gravitational waves. And since then, I'm involved in the Kagura gravitational wave project. Okay, so over 40 years, I worked on these topics. And I want to tell you, all of these research were carried out essentially in the same place. Well, in the left side, I show a map of Japan, and our experiment is located there in the Rada mountain area. And in fact, in one of the mountains, there's our facility. And the right panel shows a sketch of our underground facilities. We have Super Kamiokande at very deep underground. In addition, nowadays, we have the Kagura gravitational wave interferometer in the same mountain. Okay, well, but this is just a drawing. You may not have clear idea how the real site looks like. I want to show you just one photo, which is like this. Well, okay, this photo was taken maybe in January or February. Anyway, we work in this area. Okay, now I want to talk about neutrinos, and in particular, I want to talk about Kamiokande and supernova neutrinos. But before talking about the Kamiokande experiment, I want to briefly introduce neutrinos. I'm sorry if you know everything about neutrinos, but let me talk about it. Well, neutrinos are fundamental particles like electrons and quarks. And, well, but still you have no idea what are neutrinos. Neutrinos are something like electrons, but without electric charge. In fact, this is very important. Neutrinos are particles without electric charge. Therefore, neutrinos have no electromagnetic interactions. Therefore, they can easily pass through everything, even the Earth or even the Sun. But sometimes they interact with something, very rarely. Anyway, because of feature, neutrinos can bring information of the fundamental processes at the center of the stars. For example, at the center of the Sun. In addition, I want to mention that neutrinos have three types, or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And finally, I would like to remind you that neutrinos have been assumed to have no mass. Anyway, you may wonder how we can study these neutrinos. Well, as I said, neutrinos very rarely collide with some, for example, with a nucleus. Then in this case, typically a charged particle is emitted. And in fact, we have various methods to observe these charged particles. And in fact, if this particle propagates in the water, then this particle emits photons, which is called Cherenkov photons. And of course, we can observe photons or light by photodetectors. Therefore, we can observe these light. Therefore, with this light data, we can understand that at that moment, neutrino collide with a nucleus, producing a charged particle. So this way, we can study neutrinos. Okay, now let's move on to our experiment, Kamiokande. Well, I think I have to tell you the original motivation for the Kamiokande experiment. It was actually not neutrino physics. About 50 years ago, in the middle 70s, there was a new theory, which was called ground unified theories. And these theories predicted that protons should decay with the lifetime of about 10 to 30 years. Well, 10 to 30 years is an extremely long lifetime. So, well, this is so long lifetime, therefore, well, we do not care if protons decay or no, not decay, but scientifically, we thought this prediction was extremely important. Therefore, several proton decay experiments began in the early 80s, and one of them was the Kamiokande experiment. And here I show a sketch of the Kamiokande experiment. It had about 16-meter diameter and 16-meter high, and it contained 3,000 tons of very clean water. The idea was, in this tank, there's water, and therefore there are many protons. Therefore, if proton has the lifetime of about 10 to 30 years, some of the protons may decay at that time. And at that time, 2 or 3 charged particles are emitted, and these particles propagate in the water, and therefore they emit photons, light, and therefore we should be able to observe the evidence for proton decays if we observe this light. So that was the idea. And the experiment started in July 1983. By the way, since the topic of this talk is international collaboration, therefore I have to say that initially, Kamiokande was not an international collaboration. It was a domestic collaboration. Anyway, the experiment started in July 1983. Unfortunately, the real proton lifetime was much longer than predicted 50 years ago. Therefore, Kamiokande was unable to observe proton decays. By the way, here I show a photo of the photodetectors we used in Kamiokande. The big one in the middle was used. And in fact, this photomultiplier tube or photodetector was developed for the Kamiokande experiment. And by analyzing the early data from the Kamiokande experiment, we realized that this photodetector worked very well. Therefore, soon, Professor Koshiba noted that with the Kamiokande experiment, we could observe solar neutrinos. The observation of solar neutrinos is much difficult because the expected signal is much smaller compared with the proton decay signal. About 1% of the strength of the signal is about 1% of the proton decay signal. Anyway, Professor Koshiba proposed to improve the Kamiokande detector to observe solar neutrinos. Okay, well, idea was simple, but in reality, we had to do many, many things for approximately 3 years. We had to improve the Kamiokande detector significantly. Well, I'm afraid I do not have time to talk about what we did in details. But, well, essentially, we did really many, many things and to observe solar neutrinos with the Kamiokande detector. And I'd like to mention just one thing. One of the improvement work was the improvement of the electronics for solar neutrino observation. Unfortunately, well, to be honest, I have to say that at that time, Japanese group didn't have such technology to develop electronics for the solar neutrinos. Therefore, we had to rely on our partner from the United States, from the University of Pennsylvania. So I think at that time, we started the international collaboration between Japan and the United States. And this international collaboration went well because the Pennsylvania group provided the technology that the Japanese group did not have. And in fact, what Japanese group did was just some very dirty things, as you can see with these photos. Anyway, so this way we started the international collaboration. And after 3 years of the extensive improvement work of the detector, essentially we were ready at the beginning of January 1987. Then at that time, there was a very spectacular event happened. This photo was taken in February 1987. These two photos show the Large Magellanic Cloud, which is next to our Milky Way galaxy. Then you find a star there exploded. And as I said, Kamiokande was ready at the beginning of 1987. And therefore, we looked at the data taken by Kamiokande experiment, and we found that Kamiokande observed about 10 neutrino events. In addition, the IMB experiment in United States and the Baksan experiment at the time, Soviet Union, observed neutrinos. So a total of 24 neutrino events were observed by 3 detectors. You see, the left panel shows all the data from the 3 experiments. The neutrino, observed energy versus the time is shown. So these are the old data we observed at that time. Only 24 neutrino events. But these events were already enough to understand the basic mechanism of the supernova explosion. Namely, we understood when a massive star finishes its life, the star collapses and shock wave is generated and the outside of the star explodes. So with this data, we confirmed this picture. And therefore, with this observation, Professor Koshiba received Nobel Prize in Physics in 2002. Well, as I said, we were ready in January 87. Then we observed these neutrinos in February 87. And also, I want to say, this supernova was visible by our human eye. And this kind of event happened after 400 years. So I think, indeed, we were very lucky. And indeed, many people said to Professor Koshiba that you were lucky. Then Professor Koshiba said, well, many people say I'm fortunate. However, at that time, neutrinos came to everywhere on the Earth. Only people who prepared for them were able to observe them. Well, I think this is a very important word for scientists. So I think we should not forget about his word. Anyway, I want to share one more thing. As I mentioned, Kamiokande started as a proton decay experiment. Then, due to the good performance of the newly developed world's largest 50 centimeter diameter photomultiplier tubes, photodetectors, Professor Koshiba proposed to observe solar neutrinos in Kamiokande. And finally, Kamiokande observed supernova neutrinos. So clearly, this story tells us that scientific development cannot be linear. So we should not forget about this. Okay, let's move on to the next topic. Super Kamiokande and atmospheric neutrino oscillations. Because of the success of the Kamiokande experiment, the Japanese government decided to support the Super Kamiokande project. And indeed, it is a very large neutrino experiment. It has about 40-meter diameter and 40-meter high, and containing 5,000 tons of extremely clean water. And in the right panel, I show a photo of the Super Kamiokande experiment when we constructed the detector. And you see there are 3 people on a plastic boat doing some work. And so comparing these 3 people and the other part, you see how big the detector is. And indeed, well, it's a complicated, very large detector. Therefore, in order to operate and analyze these data, we need many people, many expertise. And therefore, we formed international collaboration. At this moment, we have about 230 collaborators from 11 countries. But here, let me talk about the beginning of the Super Kamiokande international collaboration. This photo was taken in August 1992. We were at the beginning of the construction of the Super Kamiokande detector, actually just in the middle of the excavation of the underground cavity. At that time, we had the first discussion about the international collaboration in Super Kamiokande. Well, this was a very long day. But finally, at the end of the day, we agreed that the previous Kamiokande and IMB members who worked on very large water Cherenkov detectors decided to work together. And we were very happy at the end As you can see, there are many beer bottles there. And indeed, I think that this international collaboration has been very successful. And because I think the expertise from both groups were very important for the success of the Super Kamiokande experiment. And maybe more importantly, the leaders from each side trusted each other. Okay, let me talk about a little bit about scientific result. Well, from the beginning of the experiment, we decided to work on neutrino physics. And one of the neutrinos we worked on was the neutrinos produced in the atmosphere of the Earth. Well, cosmic ray particles come into the Earth, and they enter into the atmosphere of the Earth, and these particles interact with the air nucleus, and then typically pions are produced. And pions are unstable, decay to other particles, and during this decay, neutrinos are created. And these neutrinos essentially simply pass through the Earth and go somewhere, but very rarely a neutrino may interact in the Super Kamiokande detector. And then the neutrino interaction is observed in Super Kamiokande detector. And here I show one example of the neutrino event observed in Super Kamiokande. You see a ring pattern, and this is a typical signature of particle propagating in water. Okay, well, what is the physics with these neutrinos? From the beginning of the experiment, we have been thinking that by the studies of these neutrinos, we could reveal the secrets of the neutrinos. Namely, we may observe neutrino oscillations. Well, I'm sorry, I'm talking about neutrino oscillations without any explanation. Well, let me explain. If neutrinos have mass, neutrinos change their type or flavor from one type to the other. For example, in this graph, let's assume that muon neutrino is created at point 0 and begin to propagate to the right. Then at some point, the probability that muon neutrino is remaining as muon neutrinos go down. And at that time, tau neutrino is appearing. But this neutrino, if they continue to propagate, then at some point, the probability that muon neutrino is observed as muon neutrino come back to unity. And at that time, tau neutrino is completely disappearing. So this way, neutrino type changes. So this is neutrino oscillations. And if we observe this effect, we can say that neutrinos have small mass. So we studied neutrinos produced in the atmosphere of the Earth very carefully. And indeed, at a neutrino conference in 1998, we were able to report our first significant result. And here I show just one slide we showed at that time. Oh, by the way, well, in my talk today, I use PowerPoint, but in the previous century, we didn't have PowerPoint. Therefore, we had a different technology. Anyway, well, everything was written by hand. Anyway, well, there's a reason that I showed this slide. The lower panel shows the event, muon neutrino event, and the muon neutrino arrival direction is shown Well, cosine theta 1 means downgoing neutrinos and minus 1 means upward-going neutrinos. They came from the other side of the Earth. And the black circles with the error bars show the data, and the hatched histogram showed expectations, calculation result. And here in the calculation, we do not assume neutrino oscillations. Then you can easily find that for downgoing muon neutrinos, the data and the expectation agreed very well. On the other hand, for upward-going neutrinos, neutrinos coming from the other side of the Earth, the number of events observed was only about half of the expectation. And of course, this can be interpreted very well if we assume neutrino oscillations, namely, neutrinos produced in the other side of the Earth must propagate inside the Earth, but while propagating, they change their type. And therefore, when they arrived at the super Kamiokande detector, the probability that muon neutrino is remaining as muon neutrino is just half. So this way, we were able to convince the global neutrino community that neutrinos oscillate. Now, well, okay. So far, I simply described what we did, but let me talk about the story behind the discovery. In fact, already around 1986, in Kamiokande, we found that the observed number of atmospheric muon neutrinos was significantly fewer than expected. But in Kamiokande, we were unable to know what was the cause of the missing neutrinos. And it was clear we needed a much larger detector. Therefore, we needed the super Kamiokande detector. And at the beginning of super Kamiokande, the analysis team was separated into two. We called on-site and off-site groups. It's clear, Japanese group and the United States group. But however, soon, in about a year, we decided that all the people work together in super Kamiokande in the data analysis. And the unified international analysis group was very efficient in producing scientific results, and indeed was able to provide the evidence for neutrino oscillations in 2 years after the start of the experiment. So again, I would like to stress the importance of working together. Anyway, after the discovery of neutrino oscillations, the global neutrino community has been really working to understand neutrinos better. So here I list the neutrino oscillation experiments until now. So first of all, you see there are many experiments. And indeed, I want to stress that global neutrino community is in fact working together to understand neutrinos better. Now, you may wonder why neutrino mass is so important. Of course, electrons have mass, quarks have mass. Well, in a sense, it's natural that neutrinos have mass. Why we are so excited? Well, let me talk about this. Now, here I would like to convince you that we are indeed excited with the neutrino mass. Here I plotted the mass of charged leptons, electrons, and muons, and tau In addition, there are 6 types of quarks. Their mass are shown by blue and green circles. Now, after more than 25 years of global effort, we understand the neutrino mass rather well, and therefore, I'd like to plot the neutrino mass. They are here. So, neutrino mass are plotted in a separated place, but please be careful about the horizontal axis. Here, 1 unit is 100. So if there is 2 unit separation, that means 10,000. So then you can easily find that neutrino mass is approximately, or maybe more than, 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. 10 orders of magnitude smaller than the other particle's mass. So the neutrino mass is extremely small. Why? We do not know. Certainly, if we understand why the neutrino mass are so small, we think we understand elementary particles better. But at the same time, we think that the small neutrino mass might be a key to understand the universe better. And, well, you may ask why neutrino mass is related to the universe. Well, okay. Here I show a photo taken by the Subaru telescope in Hawaii. And we know all these galaxies in the universe are made of matter. There's no antimatter galaxy that we know. On the other hand, if we think about the history of the universe, we realize that we do not know why the present-day universe is dominated by matter. Well, 13.8 billion years ago, the universe began with Big Bang, and the Big Bang universe was extremely hot. Well, in fact, in the extremely hot universe, we know that always particles and antiparticles are created simultaneously. Therefore, the Big Bang universe was filled with the equal number of matter particles and antimatter particles. Then, universe expands and cools down. Then, it is no more possible to create particles and antiparticles. Instead, if particle and antiparticle meet, they annihilate, disappear. Therefore, we naively expect there should be no particle, no antiparticle left in the present-day universe. But of course, we exist. Only matter particle remained. It's indeed a mystery, and we do not know why this happened. But there is an interesting idea, theoretical idea, that neutrinos with very small mass might be the key to understand the big mystery of this matter in the universe. So, well, neutrino physicists were excited with this idea, and therefore a large neutrino project is under construction in United States and in Japan. With these large, very large neutrino projects, we'd like to know if neutrinos are related to the origin of the matter in the universe. Well, it's a bit technical, but with this experiment, we'd like to observe if neutrino oscillation of neutrinos and those of antineutrinos are different. Well, if we observe the difference, that will be the first step to understand the origin of the matter in the universe. Anyway, to observe the difference of the neutrino oscillations and the antineutrino oscillations, we expect that the effect is small. Therefore, we need very large and very high sensitive neutrino experiments. So there are two projects going on. And in fact, you may argue, do we need two very large neutrino experiments? Indeed, these two experiments are in a sense competitive, but in my opinion, a more important fact is these two experiments are complementary. They would like to observe the same effect, but the technology and other things are significantly different, and therefore we think it's very important that these two projects get the same answer with a very different technologies and so on. Anyway, I want to talk about the right side one, the Japanese project that is under construction in Japan. Well, it is called hyperkamiokande. It is in fact going to be even significantly larger than the present super kamiokande experiment. Well, it will be about 68 meter diameter and 72 meter high. And here I show a photo of the construction of the hyperkamiokande detector. Well, the excavation was finished in July last year, and now the water container is under construction. And well, at the bottom, you see various very large cars and instruments. And from this, you can find how big the detector is. And indeed, in order to construct, operate, and analyze the data from this detector, we need many people. We need brains. So hyperkamiokande will be an international collaboration of about 650 people from 23 countries and regions. So clearly, really, international collaboration is essential to carry out these kind of large-scale experiments. Well, I'm afraid I spent too much time. Let me quickly talk about gravitational waves. Well, first of all, what are gravitational waves? In 1916, slightly more than 100 years ago, Albert Einstein predicted gravitational waves based on his theory of general relativity. Well, gravitational waves are very small effect, but we expect a strong gravitational wave can be emitted in special cases. In special cases, for example, if two black holes form a binary star system, then rather strong gravitational wave will be emitted. And in order to observe gravitational waves, we use laser technology, interferometer technology. Because if a gravitational wave comes, the expected effect is the change of the length between two things. And in order to observe the length change, the laser interferometer is really an extremely good technology. So we use very large laser interferometers to observe the effect of the gravitational wave. And indeed, slightly more than 10 years ago, gravitational wave was observed for the first time by the laser interferometers in United States. And the upper left curve figure shows the data observed by these two laser interferometers. And well, clearly this was a really great discovery. And indeed, already in 2017, Nobel Prize was awarded to these three people. So that was about slightly more than 10 years ago. But since then, the number of observations of gravitational wave events was increased substantially. This slide summarizes the observation of gravitational waves until January 16, 2024. More than 200 events were observed. Oh, by the way, sorry, I have to tell you. Blue circles show the black hole, and the vertical axis shows the mass of the star in solar mass unit. So, LIGO in United States and Virgo in Europe observed many gravitational wave events. And so most of them are merger of the binary black holes. In addition, they observed merger of binary neutron stars and so on. But anyway, just I want to mention that since 2015, the number of gravitational wave events have been increased really substantially. And well, I don't have time to go into details of the science with the gravitational waves, but anyway, this is a quite unique way to observe the universe, to understand the universe. Therefore, at present, we are working in the Kagura gravitational wave project. It is, again, an international collaboration. We have about 150 authors of the Kagura papers, and they came from 9 countries and regions. And here I show a sketch of the Kagura laser interferometer. It is indeed a very large laser interferometer and located in underground. The arm length is 3 kilometers by 3 kilometers. And well, the project was approved in 2010. And since then, for about 10 years, we worked hard to construct the Kagura detector in underground. For example, in 2015, we finished the installation of 3-kilometer vacuum tube. In addition, we installed various mirrors for the laser interferometer in a very clean environment. In addition, we use 23 kilogram sapphire mirrors, and these mirrors are most important element in the Kagura laser interferometer. Anyway, after the initial installation of this instrument, we started to work to observe gravitational waves. But let me tell you, well, I don't have much time to talk about the details of the instrument, but this kind of instrument is extremely complicated. And therefore, really, we need a lot of brains. Therefore, we work together in the Kagura collaboration. And this photo was taken in December last year at the Yonsei University in Seoul. At that time, we had a Kagura collaboration meeting. By the way, well, although I said international collaboration, but most of them are East Asian country people. So therefore, well, from this figure or photo, you may not understand that we are really international collaboration. Anyway, so we have been working hard. In addition, I want to mention that, in fact, we are working in Kagura, but at the same time, we are working together with the LIGO scientific collaboration and Virgo collaboration. For example, to determine the location or direction of the gravitational wave source, we need at least 3 detectors which are located far apart from each other. Therefore, we think it's extremely important that Kagura join this kind of observation. So the gravitational wave detectors, LIGO, Virgo, and Kagura work together. Namely, we are observing gravitational wave events simultaneously, sharing the data and analyzing the data as a team. Well, to be honest, Kagura started the project much later than LIGO or Virgo. Anyway, I want to talk about the status of the Kagura experiment. Kagura rejoined the observation on June 11 last year. But, well, joining the observation last year was not easy because our interferometer was largely damaged by a strong earthquake on January 1st, 2024 at the nearby site, 100 kilometers away. But anyway, we successfully recovered from the damage and joined the observation last year. But, well, again, to be honest, we still have to improve the sensitivity further to really observe gravitational wave events. And indeed, the previous observation period was finished. Therefore, we are now working hard to improve the sensitivity further. And we are hoping that around 2029, we can improve the sensitivity significantly and begin to contribute to the gravitational wave observation substantially. And in addition, I have to tell you, all these works need really a long time. Therefore, we recognize that we have to think about our project in the 2030s. And, well, already several years ago, we started the serious discussion within our collaboration, and we decided that, we try to focus on this science. Here, in this simulation, there are 2 neutron stars. Neutron stars are compact and heavy object. The diameter is about 25 kilometers, and the mass is 1.4 to 2 times the solar mass. Very compact and very heavy stars. And, well, if the neutron stars form a binary system, then strong gravitational waves will be emitted. And, well, here in this simulation, expected gravitational wave is shown. And, well, just before the merger of these 2 neutron stars, and just after the merger of the neutron star, we expect high frequency gravitational wave. And we believe this is a very important information to understand what are the neutron stars. So, we decided, based on scientific importance and the feature of the Kagura laser interferometer, to improve the sensitivity in the kilohertz range. And indeed, we think it's a very important direction, and Kagura would like to make a unique contribution in the international LIGO-Virgo-Kagura network. That means, in addition to working together with the US and European colleagues, I think it's very important to have a unique contribution as the Kagura laser interferometer. Okay, well, let me summarize. So far, I talked about my research experience on neutrinos and gravitational waves. And I think neutrinos and gravitational waves are exciting scientific fields. However, to produce significant results, we need large and complex detectors with many cutting-edge technologies. To construct and operate these detectors and to analyze the data from these detectors, we have been forming large international collaborations, and we work together for science. And finally, well, this is nothing to do with my talk, but well, there is some relevance. Well, even amidst the outrageous actions of politicians lacking humanity, I believe that scientists should work together to advance science and to show what humanity should be. Okay, that's all from me. Thank you very much.
Okay, so we open the floor for questions, and then there are microphones in front of you. For those, you raise your hand, and then when your turn to talk, you press the button and then talk to the mic, so that the rest of the room is audible. Yeah. So anybody like to volunteer the first questions? Yeah. Yes, please. Yeah.
So,
Yeah.
your fellow Nobel Laureate, Professor McDonald, mentioned at the end of his talk that this kind of big international collaboration really sets a good foundation and as an example for if we are talking about the final goal is world peace, then it's possible for other parties or other fields to collaborate like this. So what's your personal view about this success in collaboration may be used in other contexts? Thank you.
Other context. Well, okay. I'm afraid I'm not a person always thinking about the international collaboration in other contexts, but I'm simply hoping that the international collaboration in basic science could be a good example for other people. That's what I'm always thinking.
Any other questions? So now, much. So you okay?
So thank you for a nice talk. So I have a question about the 2030s plan for the future Kagura plan. Mm-hmm. So I think in previous discussion, including the KIW in Taiwan, so we have a lot of future possibility discussions. And I know NTHU, Academia Sinica, and also have a lot of contribution about the calibration, high power, and also squeezing. And do you have anything, comments or some possibility to upgrade for the future? This is because squeezing and also such kind of studies, key technologies, I think.
Yeah, thank you for this question. In fact, in order to enhance the sensitivity in the kilohertz band, it's very important to reduce the so-called shot noise, which is a kind of quantum noise. And therefore, key technologies we have to implement is the high power laser, but that is actually not enough. And therefore, we need a very efficient squeezing. And in fact, we have already formed a team to push this technology. And in fact, the leader of this group is a professor at the National Tsinghua University. So really, Taiwan's contribution to the future of the Kagura interferometer is, I expect, really significant.
Yes, other questions? So we have discussed hardcore science and also the context of international, being international and then collaboration. So anything that part of the audience would like to share along those lines? Yes, please, yeah.
This is a fascinating story. The question I have is about this Kamiokanda experiment. At the initial phase, you said that it was the domestic collaboration to start with. So how scientists in Japan convinced the government to invest such a large budget to build up the underground experiment? I guess that was the beginning of the successful story. But how that event was started?
Thank you. It's a very important question. In fact, many people thought the observation of proton decay is really an important topic. And therefore, people were excited. And therefore, many people, not only experimental physicists, but theoretical physicists, pushed the Kamiokande experiment. And in fact, Kamiokande was not recognized, I believe, by the Japanese government. Instead, people tried to find money from various places. For example, that was a collaboration of the University of Tokyo, Department of Physics, Institute for Cosmic Ray Research, and KEK High Energy Accelerator Lab. And they somehow tried to find money and tried to contribute to this experiment. Of course, at the same time, we had to excavate the underground cavity. And for that, we really needed government recognition, government money. And for that, indeed, we asked government. But that was, at that time, was only a relatively small amount. So, in summary, because of the recognition of the scientific importance, people tried to realize this experiment in some way. And this way, so without trying to convince government, just simply try to start the experiment as soon as possible.
Yes, well, a good lesson for many of us. Yes, and any questions, comments? Maybe Kajita-san, I raise a question. So on the international collaboration context, it's a very collaborative, the way to collaborate is a rather broad sense. For instance, in the Kamioka story, there are different generations. In the Kamioka time, so they are competitors with IMB, but you also collaborate in being complementary. But then in the Super Kamioka time, everybody looks at you on the results, and then it's within the collaborations that is all the results are from this group, and then now evolving to Kagura, then every group produce data and put it on a table, and the world will try to make sense out of those data. So this is a different collaboration mode. Yeah. So as a physicist, as a player, to produce this and then to go through that. Can you comment on or shed some insights on how is it different or similar?
Okay, well, thank you for this question. I think, well, let me talk about the similarity. well, we are scientists, therefore we have our scientific goal, and we always share the scientific goal.
Yes.
And that is, I think, motivation for the international collaboration. But really, without any scientific sharing, without sharing scientific goals, I think we cannot have a successful international collaborations. But of course, the way of collaboration depends very much on various factors, including the size of the collaboration and so on. So for the details, I cannot say much.
Yes, okay, thank you. But I agree with you that everything should go have a shared passion on something to solve a problem. Yes, but how to do it is of course the $1 million question. So yeah. Yes, okay. Any further questions from the audience? So
I still have a follow-up question. I feel this is really unusual from the scientist in the life science point of view, because as you said, you could ask people in physical sciences to reach to the consensus so that you can go for the same direction and look for the resources to put things together and build up the first underground experiments. But for scientists in the life science division, we normally work individually. Mm-hmm. It's rare for us to make such a group and resolve a big question. So from your perspective, is this very special for physical sciences, or in the life science division, maybe we can also think about the same mode?
Well, okay, I don't know about life science, but well, certainly even in the physics community, the collaboration gets bigger and bigger. And I don't know life science, but maybe in life science, well, so far people worked individually, but begin to collaborate for a big scientific target. So I expect in the future, even in life science, the collaboration could become even more usual, and the international collaboration could also be normal. I hope that could happen.
Yes, there was a question. There was a question there.
I'm just interested. Is there a time where, in your experience of working in like these projects with so many different types of international collaboration, is there any time that you experienced a challenge with that collaboration, and how did you change your approach with your collaborators to overcome that?
Oh, okay. Challenging collaboration. Well, in the middle, I discussed, told you that at the beginning of the super Kamiokande data analysis, although we had a collaboration, but the analysis was separated into two. And well, certainly it was a challenge that, well, first of all, the separated analysis was, to me, not a way that we should go. Therefore, I really wanted to have a unified group. Therefore, to me, that was a challenge to really unify the international group.
But to follow that, but how in the process, in this case, that you make this important transition?
Well, certainly, I think both sides have to agree that we should work together. And the fact was, well, people had two independent analyses, but soon people realized that essentially we get the same result. There's no reason to have separated analysis group.
Okay. Yeah. Yes, this is also an interesting story. Not something that you can read from a journal. Yeah. Yes. The story. Yes. Yeah. Okay. So also there's a question there.
Yeah. Thank you, Professor, for your nice talk. I have some more question. You mentioned about the Kaggle. Because of the earthquake, they have damaged. If you want to develop more larger facility in Japan, the earthquake is very often in this area. So how do you overcome this kind of difficulty?
Yeah, thank you. Well, first of all, we do not have any plan to construct the even larger facility. But on the other hand, we would like to operate the Kaggle laser interferometer at least for another 20 years or so. Therefore, we have to think that we have to improve the detector itself so that even a strong earthquake comes, we do not have such a catastrophic problem. Well, there are some ideas. Some of them will be implemented rather soon, but we are not sure when we can really finish all these improvements. We have too many things to do in order to simply improve the sensitivity. Maybe our first priority is improve the sensitivity. Then we'd like to make the detector robust against the earthquakes.
Any further questions? If there are no, there's one more. So there's a precious occasions to make good use of.
Thank you, Professor, for the very nice talk. I have a question that on this slide you mentioned, I believe that scientists should work together to advance science. However, I'm sorry to say that in the scientific world, there are a number of disappointments, like scientists have their own ego. Sometimes they don't feel open to accept your opinion or to give you the chance or the change. So how, when you were young in your life, so how you deal these kind of challenges when you were young, not now, because now you have status, when you didn't have this status at that time?
Thank you. Well, okay, yeah, certainly these kind of things are happening. However, I believe we always have to have our mind like this. That's what I want to say. I don't have any good answer to your question. I'm sorry.
Yes. Okay. So there's no magic answer, but the question is well raised. Yes. Yes. Okay. Any further question? Yes. There's one more.
Hello. Okay. So you stay. Your collaborative projects, they last many years, right? Maybe even they span maybe even decades. But we've also witnessed that political climates, they change rather quickly. During your time as someone who organizes these collaborative projects, have you ever experienced maybe some sudden conflicts of interest between the researchers collaborating because of maybe some political interference or something? And how, if ever, did you deal with these problems?
Yeah, thank you for this question. In fact, I didn't discuss anything, but certainly we have been extremely fortunate because Japanese government has been consistently supporting these projects for many years. For example, Super Kamiokande started the observation on April 1st, 1996. That means Super Kamiokande has been observing for more than 30 years, just 30 years. And during this period, government consistently supported us. Therefore, we were able to keep the international collaboration in good shape. Therefore, I think, indeed, government support is extremely important.
Any further questions? If not, then I just make a small promotions that tomorrow Kajita-san would be at the Institute of Physics, which is down the road at 2. There would be another public talk where everyone would be invited. There, in that occasion, he would delve more into the Kamioka story. So probably beyond the more details on the field experiments that's been mentioned, and also at some others. There are some very good results, which is barely mentioned here. Maybe we will learn more about tomorrow. So, and then so we'll close the session for today. Well, we thank our speaker again, and then we thank all our guests, especially those outside from AS to come and join these occasions. So let's give our speaker another round of applause. Thank you.